This question's got to do with hydrostatic pressure. Hydrostatic pressure. And we know that that's equal to rho g h, where rho is the density, g is gravity, and h is the depth, basically the height. So we want to find at the bottom of the Challenger Deep in the Marianas Trench, the Pacific Ocean, just off the coast of Asia there, we can say that our density is 1024 kgs per cubic meter. Okay, that's salty water compared to 1,000 kilograms or 998 for fresh water. And we're asked to find, we also have G. Let's say it's 9.8 meters per second squared. And another bit of information we have is that 1 atmosphere, so 1 ATM, not an auto teller machine, it's atmospheres, is 1.01 by 10 to the 5 pascals, which is the SI unit. So we're asked to find the hydrostatic pressure in atmospheres. So this is pretty straightforward. We just go rho GH, which is 1024 by G, which is 9.8, times the height. This is something we didn't write down over here. The height was 10.9 kilometers, which is 1090 meters. So we have that information. So by 10900, so this is going to give us our answer in pascals. So we're going to get an answer in pascals there, but we should just multiply this now by our factor, which is 1. Remember our bridge method, ATM, is 1.01 by 10 to the 5 pascals. Okay, so that's going to give us around about 1.08 by 10 to the 3 atmospheres. Ouch. I'll just remind you of what a barometer is. It's a mercury barometer. If you look over on the right here, you can see at this point we have atmospheric pressure pushing down. In this region here, the pressure is equal to 0. And we should then be able to work out what the pressure is then bearing down on that mercury pool. It's just going to be equal to rho GH, just from our pressure equation. So we should be able to say then that the atmospheric pressure P naught is equal to rho GH. So we have all of that information. We can plug that in from the expression. We've got rho, which is 1.36 by 10 to the 4. And we've got G, 9.7835. Or I think we've got less significant figures than that. I'll just get rid of those ones. And by H, which is 740.35 by 10 to the minus 3 meters. So when we plug all those things in, we get 98500 pascals. So that's in pascals. We need that in torr. So we know this conversion that 1 torr equals 1.3 133.33 pascals. So therefore, our atmospheric pressure is just going to be, well, we divide this by divide this guy by this one, and we get 98500 divided by 133.33, and we get 739 torr. So we have a 5 kilo object submerged in water, fully submerged in a liquid, not a water, liquid, and then it displaces 3 kilograms of that liquid. So how far and in what direction does the object move in 0.2 of a second, assuming there's no drag force from the liquid, which is a big assumption. So let's write down what we have. We have the mass is 5 kgs. kg. We have the mass of the water that it displaces is 3.00 kg. We've got time, 0.200 seconds. Now, if we're looking for how far and what direction does it move, then we're kind of going to be needing to find the acceleration of this object. So we're looking at kinematics, but we're going to have to draw a force diagram to be able to do this. So we can draw the force diagram. So this thing has got mass mg acting downwards. It's also got the buoyant force acting upwards. Call it FB for now. So by Archimedes' principle, the buoyant force FB is equal to the weight of the water that's been displaced. So that would be mass of water times g. So that's Archimedes' principle. So we can use our force diagram here now to balance the forces. We've got I'll just put the buoyant force there. We've got the buoyant force FB minus mg equals mass times acceleration. That is just Newton's second law. Okay. I'll point out that this is if we take upwards as positive, guys. So we always have to do that in the start. So I can replace FB now in that equation, the buoyant force, with the mass, the weight of the water displaced. So we can then say minus mg equals ma. And we're going to solve for acceleration, so we can make this a bit neater and say g outside of mass of water minus mass equals mass times a. So therefore, acceleration is equal to g mass of the water minus the mass, all divided by mass. We can put some values in for this now. 9.8. Mass of the water is 3 minus the mass of the object, 5, divided by 5. And this equals 3.92 meters per second squared. Great. So we have the acceleration now, and this should be a minus sign as well. So this means that, well, we're accelerating downwards. This means that the buoyant force isn't enough to push us against the gravity. So we have a few things now. We've got the acceleration, negative 3.92 meters per second squared. We've got the initial velocity, 0 meters per second. We've got the time, 0.200 seconds. Well, so all we need to find now is the displacement. So we'll call it delta y. That's what we're looking for, and we have an equation that says delta y is equal to v naught t plus at squared on 2. That's going to disappear, and we can rearrange for that, or we don't need to rearrange, we just have to put some values in now. Get minus 3.92 multiplied by 0.2 squared, divide by 2, that comes out to be 0.0784 meters. And it's a minus sign, which means we're displacing in the downward direction. So in this scenario, we have a flooded basement. There's a window 3 meters off the water line, and we're going to use a pump to pump that water out and through that hole, through that window. And the height difference there is 3 meters. So the water's pumped steadily out at 5 meters per second through a 1 centimeter radius piece of tubing. What's the pump's power? So what power does the pump have to supply to be able to pump that water out? So let's suppose that the mass of the water that we pump out is delta M, is mass of pumped water. And it does it in a time delta T. It's time taken to pump. Then what's this pump doing? Well, it's increasing the potential energy of the water by raising it up. It's also giving it some kinetic energy. And what's doing that is the work required to do that. So the work, so delta W, is equal to the change in potential energy of the water plus the change in kinetic energy of the water. So that's going to be delta M GH plus half delta M V squared. Okay, which equals delta M, so GH plus half V squared. To get the power, remember, it's the work done, the change in energy over time. So we just have to take this expression now and divide through by time. So we get delta M over delta T, GH plus half V squared. Now this term here is termed the rate of mass flow, so it's the mass flow rate. Just write that over here. That's the mass flow rate. So we know also that delta M over delta T, the mass flow rate, is equal to the density of the water times the area times the velocity, cross-sectional. So this is just from our continuity equation. Okay. So this term here is the volume flow rate, RV. So we can rewrite this then and say the power is equal to rho W A V GH plus half V squared. And this equals rho water. The cross-sectional area of that pipe is just pi r squared times velocity GH plus half V squared. We have everything we need to put into that now. So we can put in 1000 for density, pi r squared 0.01 centimeters squared. The velocity is 5 meters per second, 9.8 times 3 plus half 5 squared. And this equals 66 watts. We've got a reservoir here connected to a generator building by a piece of tubing that has an intake and an outlet. So the intake here has a cross-sectional area of 0.74 square meters, and it's got a velocity there at the intake of 0.4 meters per second. We also have this height D, 180 meters. So the intake is 180 meters above the outlet. We also have that the velocity at the outlet, 9.5 meters per second, but we don't have the we don't have the outlet cross-sectional area, and we don't really need that. We're looking for a pressure difference. Whenever I see something like this, I start thinking about Bernoulli's equation. So remember, Bernoulli's equation says pressure 1, pressure inlet at this case, plus half rho V inlet plus rho G H inlet equals pressure at the outlet. Don't confuse that with atmospheric pressure, it's just outlet pressure, plus half rho V outlet plus rho G H at the outlet. Now, we can arbitrarily say that H here is equal to 0, so we can get rid of that part of the expression. We can now get the pressure difference, E0 minus Pi, just by doing some fun and games with our algebra, equals rho G. We'll just call Hi D now, so we know what D is, plus half rho V inlet squared minus V outlet squared. So that equals 1000 times 9.8 times 180 plus half 1000 0.4 squared minus 9.5 squared. So we didn't even need the cross-sectional area here. That comes out to be 1.7 by 10 to the 6 pascals, which is 1.7 megapascals.